C# and AI Masterclass by Edgar Milvis Volume 9, Chapter 10. Moving on to Chapter 10, Stateful Chat Sessions in Local Memory. Moving on to Theoretical Foundations. In-memory state management for local edge AI applications is the architectural discipline of maintaining conversational context directly within the application's random access memory, RAM, acting as a volatile, high-speed intermediary between the user's input and the deterministic inference engine. Unlike stateless HTTP requests where every interaction is treated as a fresh, context-free query, stateful sessions allow the large language model, LLM, to remember previous turns, enabling coherent dialogue, multi-step reasoning, and personalized interactions. This is particularly critical when running models like Microsoft's Phi 2 or Meta's Llama 2 locally via ONNX Runtime, where hardware constraints, VRAM/compute, necessitate strict control over the data fed into the model. Now, let's explore the why, the necessity of context in local inference. To understand the necessity of state, consider the amnesiac librarian analogy. Imagine walking into a library and asking a librarian, "Where can I find books on quantum physics?" The librarian points you to the correct aisle. You then ask, "Do they have anything by Richard Feynman?" If the librarian has no memory of the previous question, they cannot logically deduce that "they" refers to the quantum physics section. They would treat the second question in isolation, potentially directing you to a biography section instead of the physics section. In a local edge AI scenario, the model, the librarian, is often loaded entirely into GPU VRAM or system RAM. The inference pipeline, the request processing, is computationally expensive. Without state management, 1. Context collapse, the model loses the thread of conversation, leading to generic, non-contextual responses. 2. Token inefficiency. You would have to resend the entire conversation history with every single request, which is inefficient for local hardware with limited context windows, e.g., 2048 or 4096 tokens. 3. Latency spikes. Reprocessing the full history for every turn increases the time to first token, TTFT, which is detrimental in real-time edge applications. State management solves this by acting as a rolling buffer. It retains the conversation history, intelligently truncating or summarizing it to fit within the model's maximum context window, the context length, defined during the model's training and quantization. Turning our attention to theoretical foundations. From a data structure perspective, a chat session is best visualized as a directed acyclic graph, DAG, or, more simply for linear chats, a time series sequence. However, because we are dealing with complex logic and potential branching, e.g., editing a previous message, the underlying structure in C# must be robust. Let's discuss the data structure, chat message and conversation history. In modern C#, we utilize record types for immutable data transfer objects, DTOs, representing individual messages. A record provides value equality, which is crucial when comparing message content for caching or deduplication strategies, and it supports init accessors for immutability, ensuring that once a message is added to the history, it cannot be mutated by downstream processes, preventing prompt injection attacks or history corruption. A chat message typically contains role, system, user, assistant, content, the text payload. Timestamp, for auditing and potential TTL, time to live, eviction. Metadata, token count, processing latency, etc. The conversation history acts as a manager. It is not merely a list T, it is a stateful entity that enforces constraints. In the context of ONNX Runtime, where the input is a tensor of token IDs, the history manager must bridge the gap between human-readable strings and the model's vocabulary. Now, let's talk about the token limit constraint, the suitcase analogy. A critical constraint in local inference is the context window. This is often visualized as a suitcase. The suitcase, the model's maximum context length, e.g., 4096 tokens. The items, the tokens representing the system prompt, user messages, and assistant responses. The packing strategy, how we fit items into the suitcase. If you try to pack too many items, tokens, into the suitcase, it won't close, inference fails. If you pack only the newest items, you might leave behind essential context, the amnesiac librarian problem. Therefore, the theoretical foundation of state management relies on eviction policies. Common eviction strategies include, 1. First in first out, FIFO, removing the oldest messages once the token limit is reached. This is simple but risks losing critical early context. 2. Summarization, using a secondary, smaller model, or the same model, to summarize the oldest conversation turns into a single, summary token, or context blob, effectively compressing history. 3. Sliding window, keeping the most recent $n tokens while keeping the system prompt fixed at the beginning. In C#, this requires dynamic calculation of token counts. Since ONNX models often use different tokenizers, e.g., GPT-2 tokenizer versus Llama tokenizer, the state manager must be agnostic to the specific tokenizer, relying on an abstraction to estimate or calculate token usage. Let's discuss the inference pipeline integration. The state management layer sits between the UI, or API endpoint, and the ONNX Runtime inference engine. When a user sends a message, the flow is 1. Input reception, the new user message is received. 2. State retrieval, the conversation history retrieves the relevant context window. 3. Serialization/tokenization, the history is serialized into a prompt string. This string is passed to a tokenizer, a concept introduced in Book 8, Optimizing Local Models, which converts text into read-only memory int token IDs. 4. Attention mechanism, the tokenized sequence is fed into the ONNX model. The model's self-attention mechanism uses the entire sequence to calculate the probability distribution for the next token. The state is effectively the KV, key value, cache in the transformer architecture, which is built from the input sequence. This diagram illustrates the volatile, in-memory state interacting with the local ONNX runtime for real-time inference, highlighting that the data is lost upon application restart unless explicitly persisted to disk. Turning our attention to C# architectural patterns for state management. To implement this robustly in C#, we leverage specific modern features that enforce safety and performance. Turning our attention to 1. Immutability with record and init. Using record for message entities ensures that the conversation history is not accidentally mutated. This is vital for debugging and thread safety in asynchronous environments. Here, we define an enumeration, chat role. This is a fundamental architectural decision to categorize the different types of participants in a chat conversation: system, user, and assistant. We use an enum because it provides type safety and clarity, preventing us from using arbitrary strings for roles, which could lead to errors and inconsistencies. It also makes the code more readable and maintainable. Imagine if we just use strings, we might have user, 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 leading to comparison issues. Enums enforce a strict set of allowed values. At lines 3 to 8, we introduce a record type called chat message. This is a modern C# feature, introduced in C number 9, that's perfect for immutable data models. We're defining the structure for a single message within our chat system. The immutability of records means that once a chat message object is created, its properties cannot be changed. This is a crucial design choice for several reasons. It simplifies concurrency, no need for locks if data isn't changing, improves predictability, the state won't suddenly alter, and makes debugging easier. When you pass chat message objects around, you can be confident their content remains consistent. Now, let's explore 2. Interfaces for abstraction, the swappable concept. As referenced from Book 5, Abstraction Layers for AI, we define an interface for state management. This allows us to swap between an in-memory implementation, for fast local testing, and a persistent implementation, e.g., SQLite for long-term edge storage, without changing the inference pipeline. Here, we're defining an interface named iConversationState. In object-oriented programming, interfaces are contracts that specify a set of members, properties, methods, events, that a class must implement. This is a fundamental architectural decision for promoting loose coupling and enabling dependency injection. By defining an interface, we can swap out different implementations of conversation state management without altering the consuming code. This flexibility is crucial for testing, evolving the application, and potentially supporting various conversation management strategies in the future. For example, we might have different iConversation state implementations for different LLM providers or different memory management policies. Now, let's explore 3. Span T and memory T for token handling. When dealing with local inference, performance is paramount. Converting strings to tokens and back involves heavy allocation. We use span T and memory T, as discussed in Book 2, High Performance C#, to slice arrays of token IDs without creating new memory allocations. This is critical when managing the context window buffer. For example, when we need to truncate the history to fit the model's limit, we don't want to create new lists. We want to calculate the slice of the existing token array that represents the valid context. Now, let's explore edge cases and architectural implications. 1. The system prompt anchor. The system prompt, e.g., you are a helpful assistant, is usually static. In the suitcase analogy, this is the bottom of the suitcase, it stays there, and we pack user/assistant messages on top. The state manager must ensure the system prompt is always included in the token count calculation, even during truncation. If the system prompt itself exceeds the context window, unlikely but possible with complex instructions, the application must throw an exception, as the model cannot function without its core directives. 2. Asynchronous concurrency. In a server-side Blazor application or a multi-threaded desktop app, multiple requests might try to modify the conversation history simultaneously. While list T is not thread-safe, the state manager should encapsulate history access. Using semaphore slim or reader-writer lock slim ensures that the history is read and written atomically. However, for a single-user local edge application, a simple concurrent queue might suffice for appending messages, but care must be taken when calculating the total token count, which requires iterating the collection. 3. Token estimation versus exact counting. Before the actual tokenizer runs, the state manager often needs a quick estimate to decide if truncation is needed. Relying on simple character count heuristics, e.g., 1 token is almost equal to 4 characters, is dangerous because different models, Phi versus Llama, have different tokenization efficiencies. The theoretical best practice is to cache the token count at the moment of tokenization. When add message is called, we should ideally tokenize it immediately to get the exact count, storing that count in the chat message record. This prevents the double tokenization cost later when building the prompt. For state persistence, the what if, while this subsection focuses on in-memory state, the architecture must be prepared for serialization. Since chat message is a record, it is easily serializable to JSON. In an edge scenario, e.g., a disconnected tablet, the state manager should be able to dump the history to local storage, using system, text, JSON, and reload it upon restart, restoring the session context. Moving on to the role of iChat client abstraction. Referencing the architectural patterns from Book 4, Dependency Injection in .NET, the state management should be decoupled from the inference engine via an interface. This allows the same stateful session logic to drive both a local ONNX model and a cloud-based API, like OpenAI, during development phases. Here we define a conceptual interface, iLocal Inference Engine. This is a crucial architectural decision because it decouples the chat session logic from the specific implementation of the inference engine. Imagine you want to switch from an ONNX Runtime engine to a different one, perhaps a custom C++ binding or a different library. By using an interface, our stateful chat session doesn't need to know the intricate details of how inference is performed, it just knows it can call infer async and get a result. This promotes modularity and makes our system much more maintainable and testable. The infer async method takes read-only memory int for tokens, which is an efficient way to pass token data without unnecessary copying, and a cancellation token for graceful cancellation of long-running inference tasks, which is vital for responsive applications. Now, let's look at the stateful chat session class. This class is designed to manage the entire lifecycle of a conversation. Notice how it takes dependencies in its constructor, though not explicitly shown here. The read-only fields _state, _engine, and _tokenizer imply constructor injection. This is a prime example of dependency inversion principle and dependency injection. Instead of stateful chat session creating its own iConversation state, iLocal Inference Engine, or iTokenizer, these are provided from the outside. This makes the class highly testable, as we can easily mock these dependencies during unit tests, and flexible, allowing different implementations to be swapped in at runtime. For instance, _state will keep track of the conversation history, _engine will perform the actual large language model, LLM, inference, and _tokenizer will convert text to numerical tokens and vice versa. The chat async method is the heart of our conversational flow. It takes user input and orchestrates the entire process to generate a response. The very first step, at line 16, is _state.addMessage, chat role, user input. This is critical for maintaining the conversation's context. Without immediately adding the user's message to the state, subsequent steps, especially prompt building, would not have the most up-to-date conversation history. This ensures that the LLM always remembers what the user just said, which is fundamental for coherent and contextual conversations. Next, we prepare the input for the LLM. At line 20, _state.buildPrompt is called. This method is responsible for taking the accumulated conversation history from _state and formatting it into a single string that the LLM can understand. This often involves specific prompt engineering techniques, like adding system messages, role markers, e.g., user, assistant, and specific formatting to guide the model's behavior. Following this, at line 21, _tokenizer, encode, prompt, converts this human-readable prompt string into a sequence of numerical tokens. Tokenization is a crucial pre-processing step because LLMs operate on numerical representations of text, not raw strings. The choice of tokenizer, itokenizer, is often tied to the specific LLM being used, e.g., BPE for GPT-style models, sentence piece for Llama, and its efficiency directly impacts performance. Here, we address a significant constraint in LLMs, the context window length. If tokens length _ max context length checks if our current prompt, after tokenization, exceeds the model's maximum allowed input length. Exceeding this limit would lead to errors or truncated responses from the LLM. To handle this, at line 26, _state, truncate, is called. This method implements a strategy to remove older messages from the conversation history until the prompt fits within the _max context length. Common truncation strategies include removing the oldest user/assistant turns or summarizing older parts of the conversation. After truncation, we must rebuild and re-encode the prompt, lines 28 to 29, because the underlying text content has changed. This iterative process ensures that the model always receives a valid and manageable input, albeit at the cost of potentially losing some older context, which is a common trade-off in long-running conversations with fixed-context LLMs. With the prompt successfully built, tokenized, and constrained, we finally move to the core step, inference. At line 33, await _engine.infer async, tokens, cancellation token, none, invokes the actual LLM. This is where the heavy computational lifting happens, as the model processes the input tokens and generates a response. The await keyword indicates that this operation is asynchronous, which is vital for keeping our application responsive, especially since LLM inference can take a significant amount of time, ranging from milliseconds to several seconds depending on the model size, hardware, and input length. We're passing cancellation token, none here, but in a real-world application, you would pass a cancellation token from the calling context to allow users to stop the inference if they wish, preventing wasted computation and improving user experience. Once the LLM has generated its response, we must update our conversation state. At line 36, _state.addMessage, chat role, assistant, response, stores the model's output. This is just as important as storing the user's input because the assistant's response also becomes part of the conversation history, which will be used to build future prompts. Without this step, the model would not remember its own previous statements, leading to repetitive or nonsensical conversations. Finally, at line 38, the generated response string is returned to the caller, completing the chat async operation. This structured approach ensures that every message, from both user and assistant, contributes to the ongoing context, making the conversation coherent and stateful. Now, let's talk about theoretical foundations. The theoretical foundation of stateful chat sessions in local memory rests on the interplay between data structures, immutable records, resource management, token limits/context windows, and algorithmic efficiency, eviction policies. It transforms the LLM from a simple text completion engine into a conversational agent. By managing the conversation history, as a first-class citizen in the application memory, we bridge the gap between the static, stateless nature of the ONNX runtime execution and the dynamic, continuous nature of human dialogue. This requires a rigorous understanding of how tokens are consumed, how memory is allocated in C#, and how to architect systems that remain responsive even when hardware resources are constrained. Moving on to basic code example. We begin by importing necessary namespaces. Notice Microsoft.ml.ONNX Runtime and Microsoft.ml.ONNX Runtime, tensors. These are critical for interacting with ONNX, Open Neural Network Exchange, models, which are a standard format for representing machine learning models. This choice signifies our intent to run pre-trained AI models efficiently, often on edge devices, as discussed in the book. System, collections, generic, system, link, system, text, and system, threading, tasks provide fundamental data structures, LNQ query capabilities, string manipulation, and asynchronous programming support, respectively, which are common in robust C# applications. This block provides crucial real-world context for why state management is essential in AI applications, especially for conversational agents. Imagine a scenario like a smart appliance chatbot. If the AI doesn't remember previous turns, it treats each question in isolation. This leads to a fragmented and unhelpful user experience. This code explicitly addresses this by demonstrating how to maintain conversation history, automatically truncate it to fit hardware constraints, token limits, and prepare this state for an ONNX runtime inference session. This is a foundational concept for building truly intelligent and context-aware AI assistants, particularly in resource-constrained edge environments. Here, we declare the stateful chat session class, which encapsulates all the logic for managing a conversational state. Inside, max context tokens is defined as a private constant. This is a critical design decision. In real-world LLMs, like Phi, 3 or Llama, The context window is a fixed maximum number of tokens the model can process at once. Exceeding this limit leads to performance degradation or outright failure. By setting max context tokens to 20 for this example, we are simulating a very small, constrained environment typical of edge devices, allowing us to clearly demonstrate the token truncation mechanism. This constant directly influences the memory capacity of our AI. We define a simple chat message struct. Structs in C# are value types, which can be more memory efficient for small, immutable data like this, especially when frequently passed around. Notice the role, content, and token count properties. While role and content are standard for chat messages, token count is vital for managing the context window. In a production system, this token count would be accurately calculated by the LLM-specific tokenizer, e.g., TickToken for OpenAI models. For this demonstration, we'll use a simplified estimation, but its presence highlights the importance of managing message length relative to the model's capacity. The toString override is a small but helpful utility for debugging and logging. Here, we declare _conversation history as a list chat message. A list is chosen for its dynamic resizing capabilities, allowing us to easily add and remove messages as the conversation progresses. The read-only keyword ensures that the list itself cannot be reassigned after initialization, promoting encapsulation and preventing accidental modification of the history collection. This list serves as the in-memory buffer for our chat session, holding the entire context that will be fed into the ONNX model. The addMessage method is the core entry point for updating our session state. It takes a role, e.g., user, assistant, and content as input. The first crucial step inside this method is estimate token count, content. This highlights a fundamental aspect of LLM interaction. Text needs to be tokenized and its length measured in tokens, not just characters or words. While our estimation here is simplified, in a real application, this would involve a complex tokenizer specific to the LLM. The chat message struct is then instantiated with these details, creating a complete representation of the message that includes its estimated token cost. After creating the chat message, we add it to _conversation history. This is a straightforward operation, but the subsequent call to enforce token limit is where the intelligence of state management comes into play. This method embodies the sliding window approach, a common strategy in conversational AI. Instead of just adding messages indefinitely, we proactively manage the conversation length to ensure it never exceeds the max context tokens. This prevents out-of-memory errors or truncation by the model itself, ensuring predictable behavior and efficient resource utilization, especially on edge devices where memory is constrained. The estimate token count method provides a simplified way to measure message length. Notice the comment, in real scenarios, use the specific model's tokenizer, e.g., TickToken. This is a critical distinction. Our current implementation merely splits by common delimiters, which is a very crude approximation. Real LLMs use sophisticated tokenizers, like byte pair encoding or word piece, that map text to numerical IDs. The token count from these tokenizers is what truly matters for the model's context window. This simplified version allows us to demonstrate the token management logic without introducing the complexity of a full tokenizer, keeping the example focused on state management. The enforce token limit method is where the sliding window strategy is implemented. We first calculate total tokens by summing the token count of all messages in _conversation history. The while loop then checks if this total exceeds max context tokens. This is a continuous check, ensuring that as soon as a new message pushes the total over the limit, action is taken. This proactive management is key to maintaining a stable and performant chat session, preventing the LLM from receiving an overly long input that it cannot process or that would degrade its performance. Inside the while loop, we implement the actual truncation. _conversation history.remove at 0 removes the oldest message. This is the sliding part of the sliding window. As new messages come in, the oldest ones are discarded to make room. We also update total tokens by subtracting the removed messages token count. The console.writeLine statement is a helpful debugging tool, showing us exactly which messages are being removed. This strategy ensures that the most recent and relevant parts of the conversation are always prioritized and kept within the model's context window, which is crucial for maintaining conversational coherence. The getFormatted_prompt method is responsible for prompt engineering, transforming our structured conversation history into a single string that the LLM can understand. We use a string builder for efficient string concatenation, which is a best practice in C# when building strings iteratively, as it avoids creating numerous intermediate string objects. Notice the system instruction at line 121. This is a form of system prompt or role-playing instruction. It sets the context for the AI, guiding its behavior, e.g., you are a helpful assistant for a washing machine. This is a powerful technique in LLM interaction, influencing the model's tone, persona, and focus, and it's particularly important for specialized applications like an appliance chatbot. Following the system instruction, we iterate through _conversation history and append each message to the string builder. This is how the AI remembers the past conversation. Each message is formatted with its role and content, creating a natural language representation of the chat log. Finally, the new query from the user is appended. The order is crucial: system instruction, then history, then the current query. This structured prompt provides the LLM with all the necessary context to generate a relevant response. The output of this method is the complete input string that will eventually be tokenized and fed into the ONNX model. The runMock inference method simulates the entire ONNX inference pipeline. It starts by logging the current user query for clarity. Then, it calls getFormatedPrompt, user query, to assemble the full conversational context, including system instructions, chat history, and the new query. This full prompt string is what our simulated LLM will read. Printing this prompt helps us verify that our state management and prompt engineering are working as expected, showing us exactly what information the model is receiving at each turn. This section simulates the crucial step of converting the natural language prompt into numerical input for the ONNX model. Real ONNX models, especially for LLMs, don't directly consume strings. They expect input_IDs, a sequence of integer IDs representing tokens, and often an attention_mask, indicating which tokens are padding. Our tokenized_IDs method is a highly simplified mock, but it serves to illustrate the conceptual step. Text must be tokenized and converted into a numerical tensor. The dense tensor long is then created, representing the input to the ONNX model. The dimensions, 1, input IDs, length, mean a batch size of 1, a single prompt, and a sequence length equal to the number of tokens in our prompt. This shape is fundamental for many transformer-based models. Here, we simulate the actual inference and subsequent state update. The commented lines show what real ONNX runtime code would look like, creating an inference session and running it with named_donks value inputs. Our mock simply prints a message. Crucially, after the inference, we generate a mock response. This simulated response is then added back to the conversation history using addMessage, assistant, mock response. This step is vital for maintaining state. The AI's own response becomes part of the context for the next user query, ensuring the conversation flows naturally and coherently. This closes the loop of state management. New input update history generate prompt infer update history with output. The tokenized_IDs method is an intentionally simplistic placeholder. Its only purpose is to take a string and convert it into an array of long integers, which is the expected data type for token IDs in ONNX models. By mapping each character's ASCII value to a long, we create a mock sequence of IDs. It's important to understand that this is not a real LLM tokenizer. A real tokenizer would use a pre-trained vocabulary and sophisticated algorithms to break down words and subwords into tokens, but for demonstrating the concept of tensor creation and input preparation, this simplified approach is sufficient and keeps the focus on state management. The main method serves as the entry point for our demonstration, orchestrating the entire stateful chat flow. We start by printing a header to clearly indicate the start of the demo. Then, a new instance of stateful chat session is created. This session object will hold all the conversational state and logic. This setup allows us to simulate multiple turns of a conversation, each building upon the previous one, showcasing the core purpose of state management in an AI application. In Scenario 1, we initiate the conversation by calling runMockInference with a user query about cleaning the filter. This simulates the first interaction with our AI. The runMockInference method will handle adding this message to the history, formatting the prompt, and simulating the AI's response. Scenario 2 immediately follows with a related query: what temperature should I use? This is where state management becomes critical. If our system were stateless, this second question would be treated as a brand new query, potentially leading to a generic answer. However, because stateful chat session remembers the previous turn, about the washing machine, the AI can provide a contextually relevant response. This vividly illustrates the why behind stateful design. Scenario 3 demonstrates the token limit enforcement. We introduce a long text string designed to be verbose. Then, we use a for loop to add this long message multiple times. This action is specifically crafted to exceed our max context tokens limit, which was set to 20. By repeatedly adding long messages, we force the enforce token limit method to activate, removing the oldest messages from the conversation history. This provides a clear, runnable example of the sliding window truncation strategy in action, showing how the system dynamically manages its memory to fit within hardware constraints, a crucial aspect of edge AI development. Finally, after flooding the chat to trigger truncation, we print a header indicating the final history state. The crucial point here, as noted in the comment, is that only the most recent messages that fit within the max context tokens window will remain in the underscore conversation history. This final state is a tangible result of our token management logic. It confirms that the system successfully prioritized recent context over older, less relevant information when faced with memory limitations, which is exactly the desired behavior for a performant and resource-aware edge AI application. By scanning this code you can go to the website with more details and with buying options. On leanpub.com you can find the discounted bundle with all the volumes. This lesson is excerpted from Volume 9, Chapter 10 of the C# and AI Masterclass ebook series and from the volume Edge AI and Local Inference. Running LLMs, Llama/Phi, locally with C# and ONNX. You can find all source code here, https://github.com/edgarmilvis/C# programming series. The ebook includes 20 chapters, each one with diagrams, advanced examples, and 5 exercises with solutions. Subscribe to the channel to watch more videos. Thank you for your attention. I look forward to seeing you in the next lesson.